Math 232, Section 7.4 on antiderivatives. So today we're going to explore what an antiderivative is and hopefully flesh it out with some examples, some illustrations, and I hope it makes sense. So what is an antiderivative? It's kind of what you would expect, I think, if you know what a derivative is. Antiderivative just means it's the reverse process. Kind of like you would have antimatter or anti-disestablishmentarian or whatever you might be anti, is the reverse of something. And just like squaring is the reverse process of square rooting, exponential and logs are inverse processes. And so in the same way, taking an antiderivative is the reverse process of taking a derivative. So we're going to flip everything that you know about derivatives around. For example, since the derivative of 5x cubed minus 2x plus 1 is, so hopefully you know your derivative rules, and you know that we have to use the power rule here. So the exponent decreases by 1, and we bring down the 3 for the 15x squared. The 2x, so what happens to the 2x here is that it loses an x, and the constant here, so where does the 1 go? Well, the derivative of 1 is just 0, right? So any constant has a derivative of 0. So that's the derivative. Therefore, so as a result, the antiderivative, and so that's what this symbol here is. Okay, this symbol here, read as antiderivative, although this symbol should look familiar to you because we've also called this the integral. And if you're confused, if you're confused by this symbol, you say, wait a minute, I thought we just looked at this and said that this was area, right? Well, kinda. So area, let me write in the margins here. So area was the definite integral, right? And we had limits. And sure, we used the same symbol, the same integral symbol. But area was a definite integral. And this is an indefinite integral. Okay, so there's no a to b here. And so this symbol is used to symbolize the antiderivative. And you say, well, why do they use the same symbol for both things? That's a great question. Hold your britches, hold on tight, because you'll find out soon enough. So, the antiderivative of 15x squared minus 2 with respect to x should be, well, what do you think it is? That's right. It's the cubic that we started with back here. So it's just reversing the process, okay? And yeah, so the symbols, so we have this this integral symbol right here. The dx is sort of the bookends of this. Sometimes we put parentheses around this to show that that's the function that we're integrating. And therefore this is the antiderivative, right? Well, kind of. So let's see where all the things come from, right? So how do we get that? Because we know the power rule for derivatives. So what happens here with the antiderivative? Well, so how did this 15x squared here become 5x cubed? Well, so if over here, if in the derivative we decreased the exponent by 1, then when we take the antiderivative, I guess we're going to increase it by 1, right? So if up here we subtracted 1, here we're going to add 1 to it. So a squared becomes a cubed. What about the coefficient? How did the 15 become a 5? Well, When we took the derivative, the 3 came down and was multiplied by the 15. So here we multiplied by 3. So in this case, we actually end up dividing by 3. So we divide the 15 by 3. So where does the 3 come from? Well, 3 is this new exponent over here. So it's kind of thinking all in reverse of what we're used to. What about the minus 2 here? How does that become 2x? Well, so remember that back up here, when you took the derivative of 2x, it just lost its x. So this is kind of like a country song where you get your x back, right? And so the 2, the constant 2, when you integrate, it just gains that x next to it. Okay, so that's what we do with constants in integration. But what about the 1? So you say, like, what happened to the 1? Well, up here, the 1 became a 0, so there wasn't anything in the integral. How do we get the 1 back? And the answer is, well, we can't. We can assume that in the process, if this is the derivative of some function, that in the process that a constant would have gotten lost, but we can't really get it back in the integration process. So what we do is, instead of writing the plus 1, we're just going to write plus c, meaning that there could have been a constant here that we were trying to work backwards from. We just don't have any way of knowing what that constant was just by looking at the integral, right? Obviously up here, if we know this part, then we can know that it's 1. But without that initial statement, there's no way to work backwards from this integral and know that what the constant was. So we're going to write plus c at the end of every integral, okay? Always. Are you going to forget? Absolutely. Am I going to remind you? Always. Okay, so you always want to remember to write your plus c. In general then, if the derivative of big F is little f, then big F is the antiderivative of little f plus c. Okay, so that's sort of the way you should think about this. So what's the rule? Do we have a rule for this? Well, so far we've used the power rule, and if you recall, the power rule for derivatives looks like this, and you decrease the exponent by 1, and the exponent then comes down as a coefficient, right? So we have that power rule. So therefore, we also have a power rule for antiderivatives. So, and we summarize that kind of right here. So for antiderivatives, instead of the exponent decreasing by 1, the exponent is going to increase by 1. And instead of multiplying by that exponent, we're going to divide by not the original exponent, but the new one that we get. So the power rule for antiderivatives looks like this. Okay, and you see here that we are increasing the exponent by 1, and then we're also dividing by whatever that new exponent is. That same number ends up being on the denominator. And of course, don't forget plus c. So if you look in your packet, you will find a whole list of derivative rules, which you already know. And so now we're just going to kind of try to flip them around and see how they work in reverse. So the next one here is the product rule. So the product rule for derivatives kind of has these different terms, and it's possible that you would recognize an integral as the result of a product rule, but this doesn't really happen a whole lot. It's not very common. Some people, later on you might learn about integration by parts, where this is used as a tool, but for now I'm just going to say that there's no product rule for integration. Okay, so we don't have a rule for how to handle the antiderivative of a product. Your best bet is to try and simplify the expression that you're integrating, and we'll see that in the examples. Same with the quotient rule. Okay, so you might recognize an integral as matching a quotient rule exactly, but the chances of that are slim. So instead, we're just going to say there's no quotient rule for antiderivatives, and your best bet is to try and simplify the expression. And the goal, I guess, of simplifying is to go back and use the power rule. The chain rule. So this is your chain rule where you have composition, and you first take the derivative of the outside function and then the derivative of the inside function. So this one actually does have a reverse process, and we'll learn this at the end of the video, and it's called U substitution. And so we'll take a look at what that looks like and how to recognize it. The inverse of the derivative of e to the x, since the derivative of the x is e to the x, then can you guess what the antiderivative of e to the x is? That's right, it's still e to the x plus c, of course. Here's a few more. If the derivative of natural log is 1 over x, then the antiderivative of 1 over x is natural log plus c. With the trig functions, more of the same. If the derivative of sine is cosine, then the antiderivative of cosine is sine, and the antiderivative of sine is negative cosine. So are you going to get these mixed up? So these four here, are you going to get them mixed up? You may. It is possible that you would get them mixed up. The general guiding rule is that, yes, the derivative or antiderivative of sine is cosine, cosine is sine. So what you need to remember, though, is when to apply this negative. Okay? And if you already know that the derivative of cosine is negative sine, then that might help you to remember that the antiderivative of sine is negative cosine. So it's certainly different than the derivative rule, right? So the derivative of sine is just regular cosine. So the antiderivative of sine is not regular cosine, it's negative cosine. Okay? So anyhow, that's the rule. The antiderivative of secant squared is tangent. That one doesn't come up very often. And last property here is, I like to mention linearity. All that the linearity property really says is that both derivatives and antiderivatives are nice to work with, meaning that coefficients can just be treated as coefficients, right? So like if a is a coefficient of function f here, then it is also a coefficient of f prime. And so the same is true here in antiderivatives, that if a is a coefficient of function f here, then I can actually pull it out of the integral and just treat it as a coefficient of the antiderivative of f. Okay, so coefficients are nice, and also addition and subtraction is nice, right? So if you have a plus between functions, then you also have a plus between derivatives. And so over here, if you have a plus between functions, then you will also have a plus between their antiderivatives. Okay, so that's just the niceness of derivatives and antiderivatives alike. All right, so a few examples. What is the antiderivative of this quadratic? Well, so here we'll apply the power rule. So you'll increase the exponent by 1 and divide by that new exponent. So 3x squared becomes 3x cubed. Okay, so there I increased the exponent by 1. And then I divided, so right here, I divided by that new exponent. Okay, and of course I'm going to simplify this, but that's just showing my work. For x, because this is x to the first, I increase the exponent by 1, and then also divide by that new exponent. And the 2, which is a constant, gains its x back. Okay, and if I do a little simplifying here, the 3's cancel out, so I just get x cubed. The 4 and the 2 simplify, the 2 and 1, and the negative 2x stays. Okay, so just applying the power rule here. Uh-oh, did I forget something? That's right, I forgot plus c. Did you forget it too? All right, so let's not forget plus c. That's going to take some getting used to. Second example, the antiderivative of sine x plus 1 over x plus e to the x. Yep, 3 different functions. Is it as simple as just applying the 3 different properties? You bet. Okay, that's the niceness of addition. This is not equally nice with multiplication, as we'll see next, but the niceness of addition. The antiderivative of sine is, so it's not cosine, because the derivative of sine is cosine, so the antiderivative of sine is just negative cosine. 1 over x, that's natural log, e to the x, and of course don't forget plus c. So third example is a product. And you're like, ooh, product. Can I just use linearity and just take the antiderivative of the 2 separately? No. And there's also no product rule. And so my suggestion was, we'll simplify. So simplifying here means distributing, yeah. And so I rewrite the integral as x cubed minus x squared. Now I can use linearity and the power rule twice. So x cubed becomes x to the 4th over 4, x squared becomes x cubed over 3, plus c. And we're done. Period. Fourth example, square root of x. I didn't see any properties with square root. What's going on? Well, just like with derivatives, we should rewrite this with a rational exponent of 1/2. Okay, the power rule works just the same here. You increase the exponent by 1. So just to show my work here, that 1/2 plus 1 is 3/2. Okay, so there's my new exponent divided by the new exponent. So divided also by 3/2. Now, it's only courteous to return our answer in the form that it was given here with the square root. So if you know the properties of rational exponents, okay, so if you know that x to the m over n is the nth root of x to the m, then you can rewrite x to the 3/2 as the square root. So where's the square root part? Well, it's here, although we usually don't write the 2 for square roots. We write it for cube roots and 4th roots and 5th roots and all the others. But for square roots, like what we had here originally at the beginning, right? We don't usually write the 2 index. So the square root of x cubed. What about the 3/2 in the denominator? What happens to this? Well, here we change division by 3/2 to multiplication by the reciprocal. So instead of dividing by 3/2, we are multiplying by 2/3. Okay, so the 2 goes on top, the 3 on the bottom. And plus c, that's our final answer. Fifth example. So here we have a quotient. Ooh, do we use a quotient rule? No, no quotient rule. Instead, simplify. So here the simplifying that can happen is that we can split that fraction into 2 fractions, because we have this nice monomial in the denominator, and so we can divide both the x and the 1 by x squared, like I have here, and that means we can simplify each of those. So x over x squared, if I cancel an x, I get 1 over x. And 1 over x squared, I can write using a negative exponent. You might wonder, well, why didn't I write this one then as x to the negative 1? Because, right, so if I did that with 1 over x squared, why didn't I do that with 1 over x? Well, 1 over x has its own rule. Remember, 1 over x is natural log, whereas 1 over x squared is not natural log. And here I use, with the negative exponent, I do the same power rule. I increase negative 2 by 1. Don't say negative 3, right? So increasing negative 2 by 1 is negative 1, dividing by negative 1 on the denominator, okay? So, but what would happen if we did write 1 over x as x to the negative 1 and use the power rule? Well, if we tried to use the power rule here, so look what would happen. We would increase the exponent by 1, and so if you increase negative 1 by 1, you get 0 over 0. That is just bad news all over the place, okay? So, in fact, this is the exception to the power rule. So we really should revise the power rule to say, except for when x is, or when n is negative 1. Okay, so the power rule works for any exponent, even fraction or decimal exponents, even negative exponents, but not, so you should not use the power rule when the exponent is negative 1. Okay, so instead we have a separate rule for that, which is the natural log. This negative exponent, then here we will switch that back to the reciprocal. The negative 1 in the denominator, we'll just change the sign there to minus, and that's your final answer. That's the antiderivative of x plus 1 over x squared. So let's talk more about what the plus c is. So we always get a plus c when we take the antiderivative, because we always assume that there may have been some constant that in the differentiation process went to 0, and we think we might want to get that constant back. But how do we get it back? So suppose that we know that the derivative of a function is 3x squared minus 3, and we want to know what the function f is, and so function will be the antiderivative of that. And so here's my power rules. I simplify the 3's here, and don't forget the plus c. So is there any way to get that plus c, to know what that plus c is? And the answer is yes, but you need to know something about the function. We need to know what's called an initial condition. So we need to know a point on that function. So what you'll do is, once you have a general antiderivative, okay, so this is what we call a general solution. General solution is that we'll take this initial condition and we'll plug it in. So since f of 2 is 1, then plugging, so what I'm doing here is I'm plugging in 2 for all the x's. Okay, so that's that and that. And having done that, I know that the function needs to equal 1. So this gives me an equation that I can solve to find c. So 2 cubed is 8, minus 6 is 2, and then subtracting 2 from both sides, we get that c is negative 1. So putting that into our antiderivative gives us what's called a particular solution. Particular solution. Okay. And so actually now we know what plus c was. And so this is the actual function whose derivative was 3x squared minus 3, and that went through that particular point. Your turn. Take a few minutes and try these 5 problems, and then unpause the video and check your answers. All right, welcome back. So I'm just going to give you the answers here and maybe just make a couple comments on them, but if you have particular questions about how or why, please bring those to class. Number 1, here I'm just using the power rule for each of those, and just remember that the 2 gets its x back, and don't forget plus c. Number 2, trying to trick you here. This 2 over x, think of it as 2 times 1 over x, and if you do that, and also this x over 2, think of that as half of x. Okay, so if you rewrite those in that way, you'll see that the first one becomes a natural log, and the second one we use the power rule. Number 3, here we have 2 radicals, a square root and a cube root, and I hope that here you rewrote those with rational exponents. So the square root as with a half power, and the cube root with a 1/3. So then you apply the power rule, increase those exponents by 1, divide by the new exponents, and then do the courtesy of returning it to the original form. Number 4, the 2 here, just think of that as a coefficient. So you could just bring the 2 out front and just worry about sine x plus 1. And then when you're done with those, just double your answer. So since the antiderivative of sine is negative cosine, so it's negative 2 cosine, and the antiderivative of 1 is x, and so there's the 2x. And finally, the antiderivative through the point, and here not only did we find each of the antiderivatives, but we also found the value of plus c by plugging in the point in for x and y and solving for c. Alright, time for our last couple examples. And here we're going to get into what's called U substitution, which is a little bit delicate, so try and follow along. So to start off here, I'm going to say that since the derivative of sine of x squared minus 1 is cosine of x squared minus 1 times 2x, and so if you're having trouble following this, this is an application of the chain rule. Okay, so because we have a composition here, we have our outside function here. So sine is the f of x, and then the inside function here is what we call the g of x. And so the chain rule says that we have to first take the derivative of the outside, and so the derivative of sine would be cosine, while leaving the inside unchanged. Okay, so that's still g of x, just like it was back here, times, and now we take the derivative of the inside. So the derivative of x squared minus 1 being 2x. Okay. So we have both the derivative of the outside and the derivative of the inside. So since this is true, then the reverse should also be true. So the antiderivative of cosine of x squared minus 1 times 2x dx should be blah blah blah. The question is, how do we get that? Is there a nice and clean way to get that without racking our brains? And the answer is, of course, yes. So this technique is called U substitution. It has multiple uses besides this one, but this is the most obvious one for us. And what you do is you begin by doing a U substitution. So this is where it gets the name. I don't know why they chose the letter U, but it seems to be universally used. So what we do is we let this inside function here, we call it U. Okay, so whatever is the inside of the most complicated part of this integral, we call that U. And as a consequence, so as a result, the derivative of U with respect to x is 2x. Which, if we do a little math, calculus algebra here, all I'm doing then here is multiplying this dx on the other side. So what I'm doing is I'm setting myself up for a change of variables. So my goal here is to change all of these x's, okay, even the dx, to a u variable. And the reason for doing that is because we will get a simpler integral. Okay, so this is what we should get. So let me show you how that happened. Because we defined u to be x squared minus 1, then I replaced x squared minus 1 with u. But also, notice that our 2x dx is also equal to du, and so I replaced that with du. Okay, so everything that had an x has turned into an expression in u. And now this integral is way, way simpler than the one we started with. It's just the antiderivative of cosine, which is sine. But not sine x, it's still sine u, because that's the variable that we're using here. And therefore I should do the courtesy of returning the variable from u back to x. And so here I'm doing the substitution, the reverse substitution, and changing u back to x squared minus 1. Okay? So this is the correct antiderivative, just like we suspected. Let me do one more example, just so that you have a couple examples to go by, and also because there's some variations that can happen. So suppose that we're trying to find this antiderivative. And again, if you look at the characteristics of this, what you'll notice, and you should notice this every time a u substitution is required, you will first notice a complex function. Okay, so a nested function, actually, I should say. Okay, so this is nested. What does nested mean? Nested means that there's an outside, the square root, and then there's an inside, which is the x cubed plus 5. Also present should be the derivative of the inside one. Okay, so you say, well, the derivative of x cubed plus 5 is 3x squared, and I don't see a 3 there. Well, we can fix that. Okay, so we can take care of a coefficient. So let's set up our u substitution. So we let u be the insidemost part of that nested function. Okay, this is what simplifies our integral. As a result, the derivative of that is 3x squared. Well, you say, well, I didn't have a 3x squared here, and I can multiply this by dx to get the dx here, but what do I do with the 3? Well, flip the 3 back to the other side with the du. So if you multiply both sides by dx, then you can also divide both sides by 3, right? So that's how we get this. And so this is going to help us to complete the substitution. So the substitution looks like this. Okay, notice that the x cubed plus 5 turned into u. And notice that the dx and the x squared, right, so these guys right here, both of them turn into the 1/3 du. Now, to integrate this is much simpler than what we started with. To integrate it, we want to simplify, so that 1/3, I can bring it out. It's a coefficient. And the square root, I'll write as a 1/2 exponent. And now I can use the power rule. So increase the exponent by 1, divide by that new exponent, and then change the rational exponent to a root, and change the divided by 3/2, change that to times 2/3. So if I multiply 1/3 by 2/3, I get 2/9, and u to the 3/2 is just the square root of u cubed. Oh, but I didn't want u, I wanted x. So the last step is to change u, okay, so u, back to x cubed plus 5. That's it.